Okay, today we are going to study the eigenvalues and eigenvectors. So if the definition is like this, so if we have a matrix, it's m by m. So in general, when you are doing a problem, m is 2 or m is 3. Because if m gets bigger, it's very complicated to compute by your hand. You can use it, compute it by computer, but you know, it's hard for you to compute by hand. Okay, so if there exists a lambda is a number r, or sometimes this is a complex number, and a vector alpha such that, okay, ax is a alpha is lambda alpha, but here you have to be careful. Alpha is in Rm, so it's a vector with an m component. So you have to be careful. Alpha cannot be 0. Why? Because if alpha is 0, you can say a multiplied by a 0 vector, you always get a lambda 0 vector. This is always right. It doesn't make sense. It doesn't tell me any information. So that's why the eigenvector is non-zero. Okay, if we rewrite this, so a alpha is lambda alpha with alpha is not 0, means that alpha is non-zero vector. Okay, we can write it in this form: a minus I lambda alpha is 0 with alpha is not 0. By what we studied, we know if we have an equation like this, we can write this is b. This equation has a non-zero solution, right? So we can, when this function has this system has non-zero solution or non-trivial solution, it has to be determinant of a minus lambda I is 0. For example, if this is 0, non-zero, you can use the Kramer rule. You can find alpha is always 0, right? So if this is non-zero, the determinant is 0, means that you can solve some alpha, which is non-zero vector. Okay, so for this kind of problem, first you have to know the definition. And the second step is, no, the second problem is that how do you find the eigenvectors and the eigenvalues. So first step, by the previous analysis. So of course you are given a, and then you compute a minus lambda I. So you get a new matrix. Okay, this is step 1. And step 2 is you compute the determinant of a minus lambda a by hand. Okay, so you get a polynomial. This is called, it has a name, characteristics polynomial of matrix A. So if A is 2 by 2, we know f lambda is a quadratic. If A is 3 by 3, f lambda is, a cubic. A lambda 3 plus b lambda 2 c lambda plus d. You don't have to memorize this. I just tell you some information. When you are doing a problem, you don't have to care about the power 2 or 3. You just compute it like you did for the matrix. Okay, and then you get a polynomial. This is step 2. So we want to find a lambda and a alpha, right? And then by the analysis of star, we know if you find the eigenvector or eigenvalue, you have to find the lambda, the eigenvector. So step 3, you know f lambda is 0, and then you can solve lambda 1, lambda 2, lambda 3, and lambda m. Okay, you may say, why do you have m? Because there always have m. You can say, how about if like this? Okay, you get a lambda 1 is 1, lambda 2 is 1. You have to count the multiplicity of the roots. Okay, you always have m eigenvectors. if you can solve this equation. Okay. Okay. Anyway, there are some that you may say, okay, how about this? Of course, there is no real roots, but you don't have to care about it. You just use the formula you know, and then you find the complex one. We will use this in the future, but if the matrix is good, you can always find the m real roots. Okay, don't care about it. You just compute. Okay, and then after you find this, you get all the eigenvalues. Okay, and then so we have to find the eigenvector. How? You just consider the equation, this double star. So after you got alpha, you can solve a minus, you already know lambda, sorry, after you got lambda, and then multiply by I. Of course, what's I? I is identity, or sometimes the book use E. Okay, they are same. Okay, sorry. So, and then you try to solve alpha I. So for each I, lambda I, you can solve alpha I. So for lambda 1, you solve alpha 1. For lambda 2, you solve lambda 2. For lambda n, or m, sorry, you solve Rm. And then, I forgot to say something. So, sorry, back. And then, after this, lambda is called the eigenvalue of eigenvalue of A, and alpha is called the eigenvector associated or corresponding to associated with lambda. Okay, so it means that eigenvalue and eigenvector are always appearing at the same time. You cannot say, okay, eigenvalue. When you're talking about eigenvalue, you have to, when you're talking about eigenvector, you have to know the eigenvalue. When you're talking about eigenvalue, automatically it has an eigenvector. Okay, two concepts are appearing at the same time. Okay, so, and then we got alpha I is the associated eigenvector associated to lambda I. So for today's work, worksheet, first you have to know how to find the eigenvalue and the eigenvector. So you just follow step 1, step 2, step 3, and step 4. So after we study the eigenvalue and we continue to study the differential equation. So it's kind of every time we have two parts. One part is about the linear algebra. Second part is about the differential equation. So for a differential equation, today you have the two applied problem. The first one is the bacteria problem. The second one is about the compound interesting problem. But two problems are the same. I just tell you the formula. Okay, in general, you have a function and you compute a differential equation. We have k and yt. You can always solve this equation by the method you know, and yt is c, e, k, and t. And also you have some initial data by this. In general, you sometimes you have to decide the k by yourself. And then in general, the y0, it helps you to determine say and other information. When you are looking at the problem, you know how to do it. So this is use the bacteria problem and the compound interest. Okay, so this is about my talk today. Okay.